Hello. So welcome to this talk on high-performance data processing in Python. So a little bit about me before we start. So I'm a software engineer that works for a algorithmic trading hedge fund called Engineers Gate. And a lot of what I do is I build out our data processing infrastructure. So we basically have a lot of machine learning models that try to predict the stock market, and then we have systems that automatically trade based on those predictions. And to do that, we need a lot of data. So I'm primarily a Python, C++, and Rust developer. All the data stuff I end up doing usually ends up in Python. And sometimes you have a lot of strict time requirements. So I put a lot of time into learning how to write Python quickly, how to write Python computation quickly. So Python is a hugely popular tool for data analysis. A JetBrains survey last year showed that half of all uses of Python is now in data analysis. So it's as popular as web development is in Python. But why? So it's high level and easy to use. There's a wealth of tools available in the scientific computing community. And in addition to that, it's a general purpose language useful outside of data analysis. So unlike MATLAB or R, where they don't tend to be used for production code, you can write all of your research code in Python and then actually run that same research code in production. So it's a great language for research. For production, so I started my sort of data science machine learning journey about 8 years ago. And the tools were sufficiently way less sophisticated at that point. Back then, people tended to think of research in Python as more of like one-off batch jobs, like large data analysis, writing a report for some company, that sort of thing. But with all the data we've got now and how machine learning is becoming so popular to implement in Python, there's this really, really strict time requirement. We need to process lots of data. We need to train them live very quickly. And the models that we're using, neural networks, even if it's just decision trees, random forests, are very complicated. So we have these strict time requirements. Now, the traditional process 8 or so years, or 10 years ago, was a researcher would build some model in their tech of choice, be it MATLAB. They would take their research code, a programmer would take that research code, rewrite it in highly optimized C or C++ if it needed to be quick. Production code is deployed, and everything works fine. Great. But in reality, what ends up happening is the researcher, who's focused on building good actual research, ends up not really thinking about the practicalities. And so the programmer that actually implements the code of production ends up looking completely different. And there's a lot of frustration. The programmer can't replicate the research results. And so there are deployment delays. And I've even seen times where there's been compromises on the model accuracy because they just needed to get it out the door quickly. So a better process is that research and production code is identical. We want to use Python because it's great for research, it's easy to use, and it makes researchers, it allows them to quickly iterate, but pure Python is slow. Even just basic benchmarks, even if they're fairly trivial, show, like for example, C is just so much faster than Python, even for like very basic computational tasks. So the solution for this is to use Python's data science ecosystem, to use packages from the scientific community. And there are a wealth of these packages. There's a lot of them. What we're going to focus on today is Numpy, which is like the fundamental backbone of a lot of these other libraries. And it's all about just computing, crunching numbers very, very quickly. So this is the foundation of a lot of packages, pandas, scikit-learn, matplotlib. And our focus is showing how to use Numpy to process numerical data really quickly. So the outline of this talk is going to be, we're going to do some analysis on a large weather data set, on a time series data set. We're going to process that data set in pure Python, speed up using Numpy, and then also use an additional tool to speed it up even further. The final solution will end up being 1,000 times faster than the original pure Python implementation. So a little bit about the data set. So there's a data set called Integrated Surface Database. This thing stores measurements like wind speed, temperature, sea level pressure across 30,000 weather stations across the globe. So there's data that even goes back as far as 1901. So a lot of that data was just manually recorded by people at weather stations, and it's sourced from over 100 sources, and it's been cleaned up for us to use. The total data volume is 600 gigabytes. To give you an example on what the data looks like, suppose we just go to one of the weather stations, which is an airport in Iran. We see that essentially the data is just a bunch of measurements every 3 hours, the weather station, and then a bunch of things like wind speed rate. Like that means, for example, 50 miles an hour was the recorded wind speed rate at that particular time. So essentially you have 35,000 weather stations, which means 35,000 different time series with different measurements like wind, temperature, and so on. So our goal is to use this data to detect extreme weather events, outliers that happen anywhere on the planet, anywhere in the history of this data. We're going to start simple and just focus on wind, and we're going to try and detect hurricanes. So we're going to use a smaller data set just for getting some performance timings. It's just the last 20 years, or 1991 to 2011. Just going to focus on wind, so the kilometers per hour that the wind was recorded, and a subset of the station. So overall, there's around 400,000 rows that we're going to be 400 million rows we're going to be processing. So how are we going to detect these hurricanes or these extreme events? So essentially, all we're going to do is find data points with unusually low or high wind speed values, so unusually high kilometers per hour. What we're going to do is, if we just have a time series like this, what we're looking for are those peaks there, the outliers, things that are unusual for that particular weather station. Now, you can't just use the same thresholds for every single weather station because different stations are in different places that are naturally more windy or less than others. So to detect an outlier, we're just going to go to every point in this time series. We're going to compute the mean and standard deviation using the last 30 measurements. And then we're going to say that the value at that particular time point is an outlier if it's more than 6 standard deviations away. So we're setting our threshold quite high. So this means that for all of this data, for all of these time series, we need to compute the moving average and the moving standard deviation. Our input is a HDF5 file. I don't have details to talk about that particular format, but it's a very efficient binary format for storing numerical data. But essentially, it has 3 columns: station ID, timestamp, when it was recorded, the weather station, and the wind speed that was recorded. Yeah. So this is simplified because the data that we have is already sorted by weather station and by timestamp. So that means that even though we have 600 gigabytes worth of data, all of the data for a single weather station is together in the same block of memory, in that all the rows are contiguous, and they're also sorted by time. We're going to have a problem with null values, so what we're going to have to do is fill in times where we don't have any values. For example, a weather station might be down. For some reason, we just don't have a measurement. So we're going to fill forward any previous values. So for example, the recording there at 6 a.m., that's going to be filled forward to the 9 a.m., which was null. The code is on GitHub. I don't have the time to really run through the pure Python implementation right now. But essentially, the crux of it is you have this big input file, 600 gigabytes, in our case, just 400 million rows, a smaller subset. We're going to split it up into individual time series for each weather station. We're going to compute the outliers, and then we're going to store all the outliers in an output CSV file. So essentially, there's these 5 steps, and when we're going to measure the speed of our implementation, we're going to measure the time for each of these 5 individual steps, which include splitting up the stations, filling forward values, computing the moving average and standard deviation, and finding outliers. So what we end up with is a CSV where we have station, weather station, timestamp, and wind speed rate, where wind speed, where that is the value of the outlier. Now, if we look at some of them, so after running the code, and we look at some of them, for example, this one, we see there's some detected outliers, and what we do is if we just Google it, so this outlier occurred at Chesapeake Bridge. We Google that, Chesapeake Bridge, 2006 hurricane, we find a hurricane, and what do you know? It actually occurred on the same time, on the 1st of September. So it works, which is great, but it took 4 hours. So the overall total time it took for these 400 million rows, a subset of the data, took 4 hours to process using the pure Python implementation. Remember that our goal is to detect extreme weather events using any measurement anywhere on the planet for the whole data set, which is 600 gigabytes. So this would take 27 days if we just use the pure Python implementation. And obviously, that's not really good. So what went wrong? So we can identify the bottlenecks by running our code using cProfile. This will output a file that we can then visualize. So we can use SnakeViz to visualize all the timings that it got on a per function level. And an example of that is if we have a simple script here, which computes a standard deviation of 100 million integers, then it would look like this if we profiled it. So this is obviously a simple implementation just for demonstration purposes, but if you run this on the cProfile, you call SnakeViz on the output, you get something like this. So you can see how long each function takes and like what in each function takes so long. So you can see how long it takes to compute the mean or square the numbers and so on. So with outliers, what we find is this. So these 5 different steps, some of them still take quite a while, like 188 seconds. Clearly, there's one big outlier here, which is calculating the moving standard deviation. Let's plot this on a logarithmic plot to make it a little bit simpler. So we have 14,000 seconds almost on just calculating the moving standard deviation. So why is it so slow? Why, even these are still surprisingly slow, like it should not take a few minutes to process the small data that we have. And there's three major reasons. The first is Python's dynamically typed, which means that every single time you perform any kind of operation, computational operation on a Python variable, Python's having to do some checks and like casts and things like that to make sure the types are compatible. Whereas in C, all you have is you know in advance, or any compiled language, you know in advance what the value is. It's not dynamic. And so that is one of the primary reasons Python is slow. It's like just every single operation, any add, anything, just takes so many more CPU instructions because there's so much more bookkeeping that you have to do. It's also interpreted and not compiled, which means that a compiler can't do smart optimizations because it doesn't know what's going to happen in advance because it's a dynamic language that's interpreted at runtime. And then finally, we have fragmented memory access, which, if you look at this in C, for example, you have an array of 9 numbers. They're all stored contiguously in memory. There's no overhead. In Python, if you just have a Python list can contain any type. So what actually a Python list is a list of pointers that then go to a different space in memory on the heap. So suddenly you've gotten this balloon of memory and overhead, and also you're accessing very different parts of RAM at different times. So it's not cache friendly. It's very bad if you're iterating for a sequence of numbers just contiguously. So it's not good. So NumPy is the fundamental package, as I mentioned, for high-performance computing in Python. There are a lot of frameworks built on top of it, and essentially what it is it has 3 main features, which is you have multidimensional array objects. So these are array objects implemented in C that are highly efficient, so you can store your data in an efficient manner. Routines, you can have very fast operations like squaring something, adding 2 vector arrays together is all very efficient and executes in compiled machine code. And you can also do efficient loading and saving of data, including stuff like HDF5, rather than having to like parse CSV files and things like that. So the core data structure is numpy.nd array, which is just an array of a fixed size and must contain the same type. So if we look at some examples, we see that the way we create an array is we can just call, first we import the NumPy module, and then we can just do something like np.arange, which will create an array from 0 to 8. So it's just creating a range of sequential numbers. We see here that we have this array and we have its contents, and we have various properties about it like shape and strides. And these actually allow very powerful manipulations that are very efficient. So to give you an example, what's actually happening in the background is a NumPy array is just a data buffer. So here we have a buffer of 9 numbers, just 9 int64s, or float 64s in this case. And then we have a shape, which describes the size of the buffer. And then we have strides, which describe how many bytes along the buffer you need to go before you hit the next element. Since we're using a float 64, that's 8 bytes, so we need to move 8 bytes along the buffer in order to go to the next element. Now, describing this as just a flat memory buffer and then having these shape and strides parameters allow you to do quite interesting things. So here, for example, this is the same data, but we just call reshape 3.3, which reshapes the 9-sized one-dimensional vector into a 3x3 matrix. And all that's happened is the shape and the strides have changed. The buffer doesn't change at all, which means that we don't even have a copy. There's no copying going on here. You can even do things like you can get rid of one dimension. So if with our 3x3 matrix, we can say, just give me the first 2 columns by just slicing it like you would any kind of Python array. And you can kind of see here, all that's changed is the shape. The data is not copied. Again, you can even slice multiple dimensions, so you can just have rows. Like you can limit the number of rows, limit the number of columns, pick what you want. And for simple slicing operations, there are no copies. So the performance benefits here compared to pure Python is that the data is stored contiguously, there's no memory overhead, you have cache locality, no copies are made for common reshaping and slicing operations, and there's fast logical mathematical operations that can execute on this buffer. So just as a benchmark, if we add 10 million numbers, we see here that in Python, we create 2 lists, 2 10 million lists, and we just add them using a list comprehension, nice and simple. If in NumPy, we create 2 NumPy arrays, 10 million integers, there's 2 ways we could add these together. Either we kind of have a similar implementation here where we have this list comprehension, where we just initialize a new NumPy array that's empty and just has all zeros, iterate through the arrays, and then just add them one by one, or we just use the built-in addition operator. And what we get are these timings. So Python takes 1 second, looping through the NumPy array takes 3 seconds, but using the built-in NumPy takes 0.03 seconds. So it's a significant speed up, it's 36 times. So what's interesting here, and this is quite an interesting point about using Python, is that NumPy with loops is the slowest of all choices here. And the reason for that is because there's so much, you're not really avoiding any of the overhead that caused Python to be slow in the first place. So what happens if you're just iterating through the NumPy arrays in Python, every single iteration you're going into the C level, into the NumPy compiled implementation, and then that's accessing the raw memory buffer, and then it's having to come back. And that's creating lots of copies, and that's just a lot of unnecessary work. Whereas if you just use built-in NumPy operations, everything's happening on the NumPy level. There's no copying going to and from the Python or NumPy level. So it's a lot more efficient. So basically, when you're using NumPy, you want to make sure you try and keep as much as possible all the computation on the NumPy level and not do any kind of explicit looping in Python. The problem with this is sometimes you want to do things where you're not just manipulating on even-sized arrays. So for example, if you want to add a 1 to every integer, we could just create a whole new vector of 1s, but that would not be very efficient. So if you had 10 million numbers and you wanted to add 1 to all of them, but you want to use the built-in NumPy addition, you would have to create a whole new 10 million size array. Or you would if you didn't have broadcasting. So broadcasting is a NumPy feature that allows you to essentially apply smaller arrays and scalars to larger arrays without any copying. So if you want to add 1, then you simply just add the 1, and then it gets broadcast to the whole array. And there's no copying involved here. And similarly, you can even do the same where if you wanted to multiply a vector by a matrix, it would know what to broadcast and just do it without any copying. And that's trivial for this example, but if you have 400 million rows, then it starts to get quite expensive. So when we use NumPy for outlier detection or use a first attempt at it, just to recap, these are the 5 different sections of detecting outliers, the 5 different steps. If we focus on just implementing one of these steps, so right now, I don't have the time to go through every NumPy implementation of each 5, but just to give you an idea on how you would use NumPy, let's think of the first step where we want to split up the file into different time series per station. So essentially what we want to do here is we have a single, in our file, in our HDF5 file, we have a single array of 400,000 weather station IDs. And they're all contiguous, so they're all in blocks together. So we just want to compute the start and end index of each station time series, so then we can use a slice into them and just get a view on the individual array when we're computing outliers for each station. The actual implementation looks like this, which is a lot of code, so I'm going to break it down. So again, suppose we have this example, very small set of data. We have only 6 measurements, 3 for 123, station ID 123, 1 for 245, and 2 for 999. What we get is this. So what we're doing here is we use Numpy Slicing, which avoids copying, to check which elements in the array change weather station IDs. So like what indices do the weather station IDs change? So we have this top level array. We have -1, which means we get all but the last element. 1, which means we get all but the first element. We compare them for equality or not equality. And then we get a bit mask. So we get an output array that's just a bit mask. False if the elements are the same, and true if they're different. And those trues indicate the indices, or the elements where the weather station changes. So then we use mp.where, which is a built-in NumPy function, to get the indices of all the true elements. So here it's 2 and 3. We broadcast by adding 1 to them to get 3, 4. And then that elements 3 and 4 are the indices where the stations change. So now, because we want the start and end indices, we need to create 2 arrays, one with all the start indices, one with all the end indices, and join them. So we just take the indices of where the stations change. We add 0 at the beginning, because, of course, that is a start index. And then we join them together to form 0, 3, 4. We do the same thing with the series ends, 3, 4, and then we have the length of the overall station IDs, the end of the array, which is 6, and then we get 3, 4, 6. So that means we have the indices that each series starts, the indices at each series ends, and then we stack them together using another built-in NumPy function called column stack, and then we get that. And so you can see here that those indices correspond to the correct slices of data. So now what we can do is we can use these indices to slice into the wind speed measurement array for each individual time series, each individual weather station. So when we do this, it's actually not that impressive with our first attempt. So we get 4 hours to 1.4 hours, and we get 2.85 speed up, which is really not a lot for what you'd expect for NumPy. You see here, for example, station ranges. By doing it in this array-based form, we go down from 42 seconds to 4 seconds. So that's a big speed up. Similarly, there's another one at the end, which is there to detect which points are outliers. That does the standard deviation check. That's gone from 250 seconds to 1 second. So you can see how fast you can actually end up going. But there's some here that are still pretty slow. Like, if anything, fill forward and moving average in the NumPy implementation is suddenly taking longer. So this is confusing because NumPy is supposed to be faster because it has no extra memory overhead, minimal copying, it's cache-friendly, so what's going on here? But the reason why it's fast is because of something called vectorization. So if you just use NumPy and assume things are going to be faster without thinking about trying to make things vectorized, you're not really going to get much benefit out of NumPy. So to take a step back from NumPy specifically, vectorization is the process of converting an algorithm to operate on a single value at a time to operate on a set of values. So modern CPUs support vector-based operations, which means that they can apply a single CPU instruction, like an add, but they apply that to multiple numbers. So to give you a concrete example, suppose you have this. So again, we want to add ones to all of these numbers. So in this case, we have 10 numbers, which means in a standard CPU with single instruction, single data semantics, it would take 10 add instructions. Whereas with CPUs that have single instruction or multiple data semantics, it's possible for them to load multiple numbers into a single CPU register and then apply a single instruction to multiple numbers at once. So in here, you can, with this specific CPU, you can fit 4 numbers in a register at once. And so by doing that, you essentially quarter the number of instructions that you have. And this is only possible when you express your data, express your operations in an array-based form. Yeah. So again, here's an example in C, actually. So ignoring Python entirely, when we add 10 million numbers together between 2 different arrays, this is a really simple implementation. We just have array A, array B, and then some out array where we store the output. Simple loop. Now we have this, which is the vectorized form, where what we've actually done is we've explicitly had a for loop that iterates in steps of 4. And by doing that, what happens is when we compile the code with no compiler optimizations, we see that the vectorized form is actually faster. It's not 4x faster, but it's faster. And it's faster because this has given enough information to the compiler for it to know that, oh, I can fit these in the CPU's SIMD registers, in the single instruction multiple data registers. So it knows it can put all 4 numbers in and apply 1 addition at a time. It's smart enough to do that. Now, a simple loop like this actually gets automatically vectorized by compilers, which is why I had to disable optimizations in order to show you the time difference. But that's essentially what vectorization is on a low level. Now, people talk about vectorization in Python in a very different way. So while it's still the same concept, you want everything to be array-based, you want to have this situation where SIMD can take effect. People tend to kind of loosely just say vectorization when they mean express it in arrays and then run all the code in NumPy, in native NumPy functions. So even if it's not explicitly vectorizable by the CPU, the concept of vectorization in Python seems to be more making sure to avoid Python loops and express everything in array-based operations using built-in NumPy functions. And we've not done that in the first NumPy implementation. So here's an example. We have fill forward. Remember, this is a thing that is going to go through our time series on each weather station and fill in empty values. This is a for loop. We've got a NumPy array. We just iterate through the array, and then every time the value is null or is nan, then we just set it to the previous non-null value, and then we keep doing that. And that's really slow because you're going in and out of the NumPy level. You have a Python loop, so there's a lot of copying going on. There's a lot of unnecessary operations and instructions going on. Now, I don't have time to go through the vectorized implementation, but you can see the main difference here is this is a for loop, and this one doesn't. And that's usually how you can tell whether or not you're using NumPy correctly. So here, everything's array-based. Everything is using NumPy built-in routines, so everything's running on the NumPy level. So essentially, I'll skip past that. We also vectorize moving average, another thing that was slow. Again, we had a for loop. It was kind of lame. It was actually slower than the pure Python implementation. Now we have an implementation that's purely vectorized, purely in NumPy. And when we do that, we see massive differences. So now we go from 2.85 to 5, we see the massive speed ups. We've got 500 to 10, 1200 to 2 seconds. So suddenly, by expressing things in just array form and just using NumPy built-in functions, there's dramatic speed up. But you see here, we still have this moving standard deviation, which is 3,300. It's faster. Before it was 12,000 seconds, but it's still really, really slow. And this is because this particular, to compute moving standard deviation is very difficult to vectorize. You can, but let's suppose that you don't have time, you need to get this thing shipped out, or you just don't think it's necessary to spend a day coming up with a vectorized implementation, a purely array-based implementation. You can use something called number. So not all algorithms are vectorizable. Some of them you're going to have loops. You're going to have some non-trivial logic that maybe is very difficult or impossible to express in NumPy array operations. So what you can do is you can compile your non-vectorizable Python code to native machine instructions. So what number is, it's a Python library. You annotate functions with decorators, and those functions will be just-in-time compiled. So what will happen is they will compile the functions to native machine instructions using LLVM. They'll apply a bunch of optimizations to them. So essentially, you're writing a Python function, but you're getting all the benefits of writing it in something like C. So number.jit is a decorator that essentially you add to a function. So if you give an example, we have sum array. This just sums up a bunch of numbers and then gives you back a result. If we just import number.jit, we decorate it, the sum array function with JIT, and we just say no Python equals true. That tells number you must compile this as native machine instructions. You cannot keep this as a Python function. And if it cannot compile the function, then it will error. It will crash. It will raise an exception. When we do that, we see massive difference. So just on this sum function, we've gone from 1.75 to 0.0065, so 6.5 milliseconds. So 270 speed up, just because we've just added one decorator. A number actually automatically reduces the types in your functions. So when you statically compile code to native machine instructions, they need to know the types in advance, which is why number has to do some kind of type inference. You can explicitly set types but, in the JIT decorator. So here we can say this function returns a 64-bit int and takes the 64-bit int as an array. But you don't necessarily have to do that. So number has some drawbacks. Like it's not a magical thing where you can just say @JIT and magically all your Python code is a few hundred times faster. For starters, number type inference sometimes fails or does something inefficient. So you'll find that you'll probably end up having to do explicit typing anyway. Some people might dislike that. I don't mind. I mean, I'm all for type annotations in Python in general, so I've got no problems annotating this. But also, you're very restricted on what you can actually do in a number array. There's a lot of Python features, even just accessing arbitrary classes, that if you want to compile with no Python equals true and guarantee you're compiling to machine code, you can't do. So it's really only meant for really simple functions that do nothing but raw computation. So when we add JIT no Python equals true to all and explicitly specify the types, we reduce the moving standard deviation from 3,300 seconds to 100 seconds. So now instead of a 5x speed up, we've got a 90x speed up. So now we have, you can see the difference in the non-logarithmic plot. We see that we have 130 seconds instead of 3,000. So to summarize, you want to use vectorized NumPy code where possible, but fall back to number code if it cannot be vectorized. Now, one last thing we can do here is we can actually parallelize this code quite easily. So to recap what we've done is we've moved all of our data to contiguous memory buffers with no Python overhead. We've run most of the computation in compiled optimized machine instructions. And we've vectorized the computation to take advantage of the CPU simmed feature, as well as just making sure everything's in the NumPy level. And we have a 98x speed up. But we do have an embarrassingly parallel problem here. Obviously, each station can be processed in parallel. So while we're computing the rolling mean and rolling standard deviation, even if that does depend on each other in each iteration, what we can do here is we can just take each individual time series and run it on a different CPU core. So we can use joblib for this. So joblib.parallel parallelizes Python loops. So wherever you've got a for loop, with heavy computation in each iteration, and that for loop doesn't have dependencies between the iterations, so each of the iterations are completely independent of each other, you can simply just use this and parallelize it. And so if you imagine after we've computed our start-end indices of each weather station, we might have something like this, where we just iterate for each start-end index, we call compute outliers, which gives us back a bunch of outliers, and we're done. That's a loop, essentially. So we can parallelize that by simply creating a parallel object. We set it to have the number of processors as number of CPU cores, because there's not really much point using any more processors than that, because this problem is CPU bound. And then we just call that created parallel processor as a function, pass it a generator, which is basically the same as the previous one, compute outliers, you're passing in wind speed, start, end. And that's it. And suddenly it's parallelized. And when we do this, we reduce it from 2.46 minutes to 1 minute. And now we've got a 177 times speed up. But that's still some overhead here, because this laptop, which is what I ran it on, has 4 CPU cores. And it's not a 4 times speed up. You never usually expect a full 4x speed up, but you do expect maybe like 3 or something like that. And this isn't quite there. So what's happening is we're actually doing a lot of excessive copies. Every single time that we run this code, we're actually extracting the wind speed measurements for a time series, and then we're copying it to a child process, because this loop is essentially running jobs on different processes. We can avoid that by using a mem-mapped file. So if we just store all the wind speed measurements in a mem-mapped file and then refer to that in all the child processes, we reduce memory overhead. So for example, here, essentially the way it works is that in your code, you have some memory that looks like it's just something in RAM to your process, but actually it's mapping to something on disk. And it's an efficient way of reading lots of data at once from disk. So we can use numpy.memmap to write it to a file, write the memmap data to a file. And then what actually happens is each worker process accesses the data from disk. So now there's only one copy. You copy it once from the mem-mapped file, rather than copying it once from the HDF5 file and then copying it again into the child process. And when we do that, we get a speed up of 291 times. So we've got 0.83 minutes, so less than a minute from the original 4 hours. Now, the final timings, what we currently have is this. So this is a logarithmic plot. So we started with pure Python. We had a bad implementation of NumPy, where we didn't really understand how to use it. It got a little bit better. We had a slightly better implementation of NumPy. We optimized the non-vectorizable code, or difficult to vectorize code, and then we parallelized. So our current speed up is 290 times. Now, one thing to emphasize is that the moving standard deviation is actually vectorizable. And we see here that in the final breakdown, the standard deviation is still the thing. So even though we've used number to optimize the for loops and the non-vectorized code, it's still never going to be as good as just running this stuff in heavily optimized NumPy routines. So I actually did implement a vectorized rolling, moving standard deviation, and there's a 10x speed up. So now, when you use that, you get 1,145 times speed up. So everything now is running in NumPy, but it's still high-level Python code. It's still easy to use NumPy routines. It's not like you've written some really hard-to-understand C, for example. So if we compare the ultimate goal, we wanted to detect outliers across the whole data. And now it's gone from 27 days to 38 minutes. So when you process the whole 600 gigabytes, we've gone down from it taking almost a month to it taking less than an hour. And this is on a single MacBook Pro. So this is without having to do any fancy parallelization or clustering, just knowing how to use NumPy and what you can optimize and what you can't can go very, very far. So that's pretty much the talk. Just to recap, Python is a great tool for research, but out of the box, Python is really slow. There's increasing demands for faster and real-time data processing. We want to use Python for this because it's great for research and great for iteration. And we want to use it in production, but Python is really, really slow and isn't viable by itself for a lot of these use cases. So trying to convert Python into some other language can often cause more problems than it solves. It's just another failure point, and it ends up delaying the deployment of statistical models and things like that. So we use it for both research and production by utilizing these scientific packages. We keep the computation in native code as much as possible. We vectorize using NumPy when you can, and when you can't, you use number to do the rest for you. You identify opportunities to parallelize. You can parallelize using something like joblib to abstract what's actually doing the computation behind the scenes. So one thing to note here is that workers can be CPU cores like we've done here, but they can actually be a machine cluster. So you can actually have workers as machines. So JobLib has loads of different backends. So you can run all your code on a single machine with multiple CPU cores first, and if that doesn't work, or if you already have the infrastructure, you can then go out to a cluster. Either way, the key thing here is the code is almost identical. So there's very, very little difference between just doing a for loop and using JobLib, and there's very little difference, sometimes even no difference other than like one line of code between JobLib using CPU cores and JobLib using a cluster. Just using NumPy numbering JobLib without any kind of parallelization across a cluster can yield thousands of times speed up. So don't just immediately give up on optimizing and just throw the problem to DevOps by parallelizing on a bunch of machines. All you're doing is adding complexity in a distributed system, which means you're still putting a lot of time into speeding up the computation. You're just not doing it necessarily in the code. So if RAM and disk is your bottleneck, parallelize using a cluster. But otherwise, you can get surprisingly far with just vectorization and sprinkling some number.jit magic. And that's the talk. Sebastian, thank you very much for listening.
Any questions?
Thanks for presentation. In general, you sometimes work not just with numbers, for example, with strings. And such techniques like parallelization and vectorization is not very good applicable for strings, for example, like regex processing. The simple task, you have a lot of text and you have regex. Have you any ideas and maybe can somehow... Yeah.
So just a disclaimer, I primarily work with numerical data, but there have been times where I've had to deal with data with strings. This isn't like natural language processing or heavy text processing, but there are times where we'll have arrays or essentially a data frame where some of the columns will be strings. Typically, you can do some strategies to basically numericalize the string. So for example, if you have some, say you have like currency as one of your attributes. So there's only like there's a limited number of currencies, and you can create a bidirectional mapping function, one-to-one mapping function between your currency code, which is like a 3-character string, and some number, some integer. And so if you do that, then that means you can represent currencies without any loss of information, but still use like a really compact, optimized integer array. One other approach, and again, we've done this where we could accept some lossiness, is actually hashing. So we've actually ended up sometimes hashing certain strings where we feel the probability of there being a collision, or if there is a collision, it doesn't really matter, it's not the end of the world. We've done that. So for example, we've had some like company ID, and we've got a lot of the IDs and they're all strings, but it doesn't really matter if there's a couple of collisions here or there because the data is so huge, and we'd rather just process it really quickly and in a timely fashion. So we've actually just hashed that. So obviously that's not like 100% theoretically ideal, but sometimes you have to be pragmatic about that kind of thing.
If I can,
Yep.
But hashing operations, they should be again parallelized and fast enough because, you know, if you have a lot of data, you need to hash it before to work with this. So it's again sometimes.
Well, it depends. So you may be able to hash it in the workers. You might be able to do it in the workers or outside the workers. Hashing is pretty fast. There's a lot of fast hashing algorithms out there. It adds some overhead, but the overhead of hashing a string to an integer, I found, is orders of magnitude faster than just using string buffers, for example. Yeah, because NumPy, I totally agree. NumPy and also pandas, for example, are notoriously, which is built on top of NumPy, are notoriously bad with dealing with strings. Yeah, so, yeah.
Okay, thanks.
Yeah, fortunately, we are out of time, so thank you, Donald.
Thank you.